wouldn't work for like math or football, where of course the parent has a clear advantage, but I think with a musical instrument, if the parent doesn't play that musical instrument, I think that's where the positions may be the most equal, right?
Right. No, in fact, within 2 or 3 years, the child will have a massive advantage.
Yeah. Yes.
Yeah. Now he even he's now 8, and he now even reads the music.
I see.
And for us, it's just not clear what he's doing and what is going on in his mind.
Yes. Okay. So I'm admitting people. Okay, hello everyone, and welcome to the last day of Prague Summer School on Discrete Math and the last lecture of Subhash Khot about hardness of approximation. So Subhash, please.
Okay, so good. So let's start. Just quick overview of where we left off in the last lecture. So this is an overview of the proof of the 2-to-2 games theorem, and so we already saw what the 2-to-2 games theorem amounts to and talked a little bit about its significance. And in this lecture, I want to say a bit more about the combinatorial modules involved in the proof. So in particular, this Grassmann linearity testing theorem, which I did present what the test is, but we'll quickly again review it. And then we will study this expansion theorem on the Grassmann graph, and we'll see this. It's simple but very nice proof that the expansion theorem implies the linearity testing theorem, and we'll probably stop there. Okay, so let me quickly go over what the linearity testing was. So here, the goal is to encode, so this is called Grassmann encoding. And here the goal is to encode a Boolean function f, little f, which is a linear function. And to encode a linear function, we write down the restriction of this function to every subspace L of dimension little l. Okay, and this encoding will denote it as this capital F. It has one entry for every little l dimensional subspace, right? And this is called the Grassmann encoding. And the testing problem is we are given a table capital F, which need not be a correct encoding, and but we want to test probabilistically whether it is a correct encoding or close to it. And here is the test, which is perfectly natural test. You pick two so you are given a table capital F. So we pick two subspaces L and L prime, whose intersection is maximal, meaning having dimension little l minus 1. And just to emphasize, we always think of the parameters as the dimension of the whole space K as being much larger than this parameter little l, which itself is also a large, very large constant. Okay, and then so we read what the table gives the table assigns a linear subspace to L. It assigns a linear subspace to L prime, and we check that these assignments are consistent on the intersection L intersect L prime. Yeah, so that's the test. Of course, it has perfect completeness, meaning If this was a true encoding, then all these entries will be restrictions of a same global linear function, and therefore everything will be consistent. Test accepts with probability 1. The test has the 2 to 2 property, meaning for every answer for L, there are exactly 2 answers to L prime, and vice versa. And the soundness, for the soundness condition, one could speculate that if the test accepts with probability delta, then maybe there is a global linear function which has some delta prime agreement with the given table, right? And here delta prime should depend on delta, and these are constants independent of the parameters little l and k, right? That's the important part. These delta prime, these are constants independent of L. But turns out this speculation, the answer is no, and we saw this counterexample, right? So let me skip describing the counterexample. But the main issue about this counterexample is are these sets called S sub x. So for a point x in the space, you could consider a set S sub x of those subspaces L which contain x, and this set has expansion 1/2. So we'll talk about the expansion in the corresponding graph called Grassmann graph. But there is a way, or at least a proposed way to get around this this particular counterexample. So we could propose that we are allowed to pick some point x and then look at only those subspaces which contain x. Okay, and then it turns out certainly for this particular counterexample that there is a global linear function g which agrees with the given table at some delta prime fraction of the spaces. And this process is called zoom in, right? That you are allowed to pick a point x and then look at only those spaces L which contain x. Now there is a dual counterexample. So this is what we didn't describe this last time. So this I will describe in detail. So the dual counterexample is you pick so the whole space has dimension k, and you pick subspaces or hyperplanes of dimension k minus 1 and distinct ones, W1, W2 up to W sub 2 to the L. So there are 2 to the L many of these for the reason that will become clear immediately. And then let T sub j be the set of all spaces L which are completely contained in the corresponding hyperplane W sub j. Okay, and for sake of simplicity, just assume that this T1, T2, and so on, these are disjoint. Now, clearly, what's the fraction of subspaces which are completely contained in W sub j? These are little L dimensional subspaces. So if they have to be completely contained in a k minus 1 dimensional hyperplane, the fraction of these will be 1 over 2 to the L, right? And that's why I took 2 to the L many of these W1, W2, and so on, so that the number of spaces which I cover is a constant fraction of all little L dimensional subspaces. Yeah, now I do something basically the same as what we did before. In the earlier counterexample, I take 2 to the L distinct linear functions, and then for all subspaces in the set T sub j, I assign them according to the function f sub j. Right. So so I have subspaces partitioned into different groups T1, T2, and so on, and then I use a different global linear function for each group. Okay, and that's my table capital F. Yeah, and then this has no significant consistency with any global linear function because I use different linear functions for different pieces or groups, right? But then this table F, it does pass the test with constant probability for basically the same reason as before. So if you try to pick a pair of subspaces L prime at random with intersection L minus 1, then since these TJs, they cover constant fraction of the subspaces, L will be in one of those stages with constant probability, which is same as saying L is completely contained in the corresponding hyperplane W sub j. Okay, and now if L is contained in W sub j, and I move from L to L prime, right, keeping the dimension of the intersection L minus 1. What's the probability that L prime will also be completely contained in W sub j? Okay. So the L prime, it just has one extra degree of freedom outside, and therefore it will also be completely contained inside W sub j with probability 1/2. Okay, and then L prime will both be inside W sub j, and both are assigned according to the same function f sub j, and the test will pass. Right. So overall, the test passes with constant probability. Okay, so this is also a counterexample. That it's a dual counterexample. And here the source of trouble are these sets called, let's call them T sub W. For a hyperplane W, it consists of all spaces L which are completely contained inside W. And these are also going to have expansion 1/2 in the Grassmann graph, which we'll come to later. And here again, we can try to get around this counterexample in the same manner. So here, let's propose that we are allowed to pick a hyperplane W and then allowed to focus only on those spaces L which are completely contained inside W. Okay, and then in this counterexample, it's clearly the case that you could pick any of these W1, W2, and so on, and just let's say I pick W1, and if I focus only on those spaces which are completely contained inside W1, I do have a global linear function, right, which explains on that piece, which is the function that would be the function f sub 1, which I used. Right. So yeah. So here is a proposed way of getting around this counterexample that if we allow ourselves to focus on spaces contained inside W for some W, and then we propose that there is necessarily a global linear function with some constant delta prime consistency. Okay, and now you can see rather easily that so we gave two types of counterexamples. First of all, you can extend these counterexamples a little bit. So, for example, instead of using these sets which consist of spaces containing a single point x, okay, you can extend these to sets which contain 3 points x1, x2, x3. Okay, so you can extend it to in this manner, some small constant number of points. And similarly, the dual counterexample you can extend by considering spaces which are contained in not quite a hyperplane, that would be dimension k minus 1, but dimension little smaller, like k minus 3 or k minus 5. Okay, so you could construct counterexamples using that, and you can even combine the two counterexamples. You can use sets of spaces L which contain 3 points x1, x2, x3, and in addition are contained in some subspace of dimension k minus 5. So you could combine the two kinds of counterexamples. Okay, right. And then you can also propose similar way out to get around these counterexamples, right? Where you are in turn allowed to focus on spaces which contain some 3 specific points and are contained in space of so-called codimension, say 5, or some constant codimension. Okay, but yeah. So maybe I lost you somewhat, right, in these counterexamples and how we propose to get around these counterexamples. And yeah, I spent so much time just to give you a sense of why we are, or just the sense of the thought process. Yeah. So if you are lost a little bit, you can simply now just look at the statement of the theorem, and this is a theorem. So it's a concrete statement, and it's a theorem, so it's a correct statement, right? So here is the statement of the theorem, the Grassmann linearity testing theorem, that for every delta, constant delta, let's say delta equals 1/10, there is a constant delta prime, maybe delta prime is 1/50, and a constant integer r, maybe r equals 5, such that the following holds. So these delta prime r, these are thought of as constants, and the parameter L, that's supposed to be a very, very large constant. right? And then the dimension k, that's supposed to be yet further large constant. So that's roughly the quantitative setting. Okay? And the theorem states the following, that if this test, this linearity test, right, passes with probability delta, meaning if the table F, right, you have consistency on delta fraction of pairs LL prime, then the following holds, that you are allowed to, there is a combination of the zoom in and zoom out. Yes, I should have stated that this process of taking a W and then considering all spaces contained inside W, we called it zoom out. So there is a combination of zoom in and zoom out, such that after the zoom in and zoom out, there does indeed exist a global linear function G, which agrees with the given table at some delta prime, constant delta prime fraction of spaces L. Okay, specifically, right, if the test passes with probability delta, then there is a subspace A of some small dimension, little a. Think of little a as like 3. And there is a subspace W of dimension k minus b, where b is a little constant, right? So it's almost the entire space, but just little smaller. Okay, and of course a plus b is at most r, maybe at most 5, and the global linear function G, such that if you restrict to only those L's which contain a and are contained in W, then you do get consistency with a global linear function, a constant amount of consistency. Okay, so that's the theorem. So let me just maybe wait for like 10 seconds just for you to read and digest the statement of the theorem. And everything we discussed before, right? The counterexamples and the proposed fix to the counterexamples, that was mostly, right, to give you a sense of how we arrived at this theorem. Okay, and if I could just hear even just from one person that this was reasonably clear, I will just proceed then. Okay, all right. So somehow nobody responded, so I will have to proceed nevertheless. But I could wait for another 5 seconds. Or we could even take a quick question if anybody has one. Okay, all right. So yeah, so let's proceed.
There is there is a question, but Carol, please unmute yourself and pose it.
Yeah, anyone who has a question, you can just unmute yourself and just ask directly. That's fine.
So Carol doesn't have a mic, but yes, so he is asking about dimension, about the statement of the theorem. So he's asking what is the dimension of L?
Yeah, so I didn't want to, get too hung up on the specifics. So think of these parameters delta prime. These are constants. Let's say 1/10, 1/50. This r will be a small integer, like maybe 5 or 10. Okay, and then this parameter L is really thought of as sufficiently large constant, maybe like 1,000 or right 2,000. And then after you fix a choice of L, the global dimension K is thought of as even much larger constant, like 10,000. Okay. So if you really want to be, get to the details, then I would say that for every delta, there is a delta prime and R, such that for sufficiently large L, After fixing L for all sufficiently large K, the following holds. Okay. Yeah.
Thanks.
Okay, so right, so let's proceed. So next we will look at this expansion question in the Grassmann graphs. Well, in the notes there is this primer on graphs and their eigenvalues and how eigenvalues relate to the expansion. Yeah, but we are not really going to need much of it in this talk. So, or for in the remaining part of the talk. So I'm mostly just going to skip it. Yeah, but I think this is the only primer where I actually write down the definition of the expansion of a set. So I will just refer to that definition. So we have a graph G, and think of it as a regular graph. And yeah, and then we need this definition of expansion of a set. So if you have a subset of vertices S, then expansion of a set, which would be denoted by phi of S, it's the probability that if you picked a random vertex in the set S, and then you took an edge going out of S, is the probability that you end up outside the set. Okay, so that's what expansion is. So for example, if you have a set such that all the edges incident on that set go outside, okay, then the expansion will be full, expansion 1. On the other hand, if the set has the property that it's completely disconnected from the rest of the graph, okay, then its expansion is 0, right? Because because you take an edge out of this set, but it just comes back to the same set, right? So you don't leave the set at all, and then in that case the expansion would be 0. Okay, so this is the notion of expansion of a set. Okay, and at least morally speaking, what you would expect is that as the sets get smaller and smaller, okay, then the expansion gets closer and closer to 1, right? Because for a typical set of very tiny size, okay, if it's a set of size, let's say alpha, let's say it's a random set of density alpha, then the fraction of edges inside would be alpha squared, right? So it gets less and less likely for it to have too many edges inside. So for a random set of density alpha, as alpha tends to 0, the expansion of the set tends to 1. Okay, so it's a simple observation, but just to keep in mind. All right, and then now, yeah, let's get to this Grassmann graph. And right, okay, so the Grassmann graph is, we basically already looked at it without actually explicitly thinking of this as a graph. So consider the following graph. There is a global space F2 to the K and subspaces LL prime of dimension little l. And in the test that we discussed, we picked a pair LL prime whose intersection had dimension little l minus 1. Okay, and that's it. Once you write down it as a graph, that's the Grassmann graph. So the Grassmann graph, its vertices are all spaces L, which are subspaces of dimension little l of some global space of dimension K. Okay, so all of these L's are vertices, and then you connect LL and prime if their intersection is has dimension little l minus 1. Okay, so this is what is called the Grassmann graph, and this was studied to some extent in combinatorics, especially in the context of what are called distance regular graphs. In particular, the eigenvalues of this graph are they were well known. So the precise eigenvalues and their multiplicities, it's a bit difficult to describe because the expressions get messy. But roughly speaking, the eigenvalues are decreasing powers of 2. The topmost eigenvalue is, of course, 1, as always, and then the eigenvalue of 1/2, 1/4, all the way up to 1/2 the L. And their multiplicities are, so these eigenvalues occur with different multiplicities, and the multiplicities are roughly speaking the 1, and then number of one-dimensional subspaces of the global space, number of two-dimensional subspace of the global space, right, all the way up to number of L-dimensional subspaces of the global space of dimension k. Okay, so these are the multiplicities. And then for every distinct eigenvalue, there is a eigenspace, right? This is the space of all eigenvectors with that particular eigenvalue. And these eigenspaces, they are mutually orthogonal. But in case since we are not going to get to the analysis, yeah, I mean, all this business about eigenvalues and right, such things we can really skip. And so here is the goal for our purposes towards the application of this 2-to-2 games theorem. The goal is to characterize all sets in this Grassmann graph that are of small size. Think of sets whose size is like 1/1,000,000, right, relative to the size of the whole graph, or maybe even less. So sets of really small size, and nevertheless, whose expansion is strictly bounded away from 1. Okay. Now, if you recall what I said just a minute before, that if you have a regular graph and if you take a random set of very, very small density, right, then we expect that with high probability, its expansion is extremely close to 1. It's essentially 1. Okay. So for random sets, random small sets, the expansion is yeah, so the expansion is essentially 1. Okay, but turns out that in this Grassmann graph, there do exist small sets, and these will be exceptional non-random sets, right? Very particular ones, specialized ones, whose expansion is strictly bounded away from 1. In fact, there are sets of expansion 1/2. There are sets with expansion 3/4, then 7/8, 15/16, and so on. Okay. So there are these families of sets whose expansion is bounded away from 1, in fact, all the way down up to 1/2. And the goal is to study what these non-random exceptional sets are. Okay. And in fact, it turns out we already saw what these sets are. These are precisely the sets called S sub x, and we also call these sets, I suppose, T sub w or S sub w. Which arose in this counterexamples to the linearity test. Okay, but let's quickly go over them again. So here is a set S whose expansion is essentially 1/2. Okay, so you can pick any point x in the space f2 to the k, a non-zero point, and let S sub x be all spaces L which contain the point x. And now, just to be clear, this set S sub x will be a set of vertices, right, in the Grassmann graph. Okay, and claim is that the expansion of this set in the Grassmann graph is essentially 1/2. And when I say essentially, it's half up to an additive term which is 1/2 to the L. Okay, and for me that is negligible, and I just don't want to write messy expressions, so I'm just going to ignore these negligible terms. Okay, and here is a quick proof, right? In fact, we even saw this proof before in different words. So what is expansion, right? You start with any vertex L in this set S sub x, which simply means that L contains the point x. And then from L, you take a random edge going out of L, meaning you take a random space L prime whose intersection with L has dimension L minus 1. Okay, and then what's the probability that the L prime is also in the set? Okay, which is same as saying what's the probability that x is contained in L prime also? Okay, and we saw that, right? If x is contained in L, and if you move from L to L prime, x still remains contained in L prime with probability is exactly 1/2, right? More or less, right? So therefore, with probability 1/2, you stay inside. Okay, and therefore the expansion is 1 minus that probability. Yeah, but 1 minus 1/2 is also 1/2, so its expansion is also 1/2 here. Okay, so I hope this is clear. And now you can extend this these sets in a little bit you can in fact pick a small number of points, x1, x2 up to x sub a. Think of a as a small constant like 3. And these are linearly independent. So these are 3 points, linearly independent points in the whole space. And then let set S sub x1 through xa be all subspaces L which contain all these points x1 through xa. Okay, I would also denote it by S sub capital A. If capital A denotes the linear span of these points x1, x2 up to x little a. Okay, so if I take a subspace capital A of dimension little a, the set S sub A, which is the same, right? It's all subspaces L which contain capital A. Right, and then what's the expansion of this set? I claim that it's 1 minus 1 over 2 to the little a, right? For the same reason, because if I take a subspace L which contains, in this case, let's say all 3 points x1, x2, x3, and then move from L to L prime, right? Now, what's the probability that all 3 points are also contained in L prime? Okay, it would be 1 over 8, because if you take the intersection of L and L prime, that is half of the space L. Okay, so the probability that all 3 points remain in that half of L, right, will be 1 over 8. And therefore, with probability 1 over 8, if you start with a random vertex in this set and take a random edge, you will stay inside with probability 1 over 8, and therefore the expansion will be 1 minus 1 over 8, which is 7 over 8, right? So in general, if you used points x1, x2 up to x little a, this is a set whose expansion is 1 minus 1 over 2 to the little a. Okay, and as long as little a is a small constant, these are thought of as sets whose expansion is strictly bounded away from 1. Okay, so I hope these sets are clear, what these sets are. Now, similarly, there are dual sets whose expansion is also bounded away from 1, and we encountered these also. But let me again describe them. For these dual sets, what you could do is again pick a point y, a non-zero point in the whole space, and let S sub y perpendicular be all those L's which are orthogonal to y with respect to the vector product over GF2, right? Or y orthogonal, it really amounts to hyperplane W, right? So it's really same as saying SW. If dimension of W is k minus 1, then S sub W would be all L's which are completely contained in W. Okay, and again, the expansion of this set would also be 1/2, because if L is completely contained in W, okay, and then you try to move from L to L prime, what's the probability that L prime is also contained in W? Okay, that's 1/2, because well, if you think of it as W as y orthogonal, then if L is already orthogonal to y, and L prime has 1 extra degree of freedom outside, right? So L prime would also remain orthogonal to y with probability 1/2 when you take L prime as a random neighbor of L, right? So this is a set of expansion 1/2, and you can extend it in a similar manner. You could take B linearly independent vectors y1, y2 up to y sub b, and let S sub y1 perp up to yb perp. These will be all spaces L which are orthogonal to the set y1, y2 up to y sub b. Okay, or a different notation would be, you can take a W. It's a subspace which is orthogonal to B vectors y1 through yb, and therefore W will be a subspace of codimension B, or of dimension k minus b. And then this same set is denoted as S sub W. These are all spaces L which are completely contained inside W. Okay, and then what's the expansion of this set? It's 1 minus 1 over 2 to the b. Okay, so I hope this is clear, because if take up any vertex L in this set, so L is already orthogonal to y1 to yb. You move from L to L prime by adding this one extra random vector or degree of freedom outside, right? So if that extra vector outside is called z, what's the probability that that extra z is perpendicular to y1, y2, yb, all of them, right? It will be exactly 1 over 2 to the b. So with probability 1 over 2 to the b, L prime will fall outside of this set, right? So the expansion of the set will be 1 minus that. So 1 minus 1 over 2 to the b. Yeah, so I hope the definition of these two families is clear, and why their expansion is this way. Yeah, so if at least one student could just, unmute oneself and just say, yes, this is what's clear, I can proceed.
Yes.
Okay, very good. All right. Then, yeah, and in general, you can combine these two sets. Okay, so what you could do is you could take A points, x1 through xa, and B points, so y1 through yb. And these are all linearly independent, and the y's are orthogonal to x's, just to be precise. And then you can consider a set denoted like this. These are all spaces L, which contain the A points x1 through xa and are orthogonal to the B points y1 through yb. Okay, and for the same reasons, this set will have expansion, which is 1 minus 1 over 2 to the A plus B. So I'm just combining the two examples together. And alternate notation would be if capital A denotes linear span of x1 through xa, and W denotes the orthogonal space of y1 through yb, and if A is contained in W, let's say, right? So dimension of A will be little a, and dimension of W will be k minus p. Okay, and then the set S sub AW is all those L's which are sandwiched between A and W, right? They contain A and are contained in W. And then, right, as I said, the expansion of this set S sub AW is 1 minus 1 over 2 to the A plus B, which is thought of as bounded away from 1. So these are special sets. So we think of A plus B as a small constant, like 5. Okay, and roughly what this Grassmann expansion theorem states is that these sets A sub AW, where this A plus B is small constant, these are essentially all the sets. Essentially, this is essentially a characterization of sets whose expansion is bounded away from 1. Right? So if A plus B is R, then the expansion is 1 minus 1 over 2 to the R. Okay, but it's a little more subtle than this. Okay, so and the subtle point is the following, and yeah, so let me. The proof is not it's not difficult at all. In fact, one of the exercises in the homeworks is designed right. It's actually geared towards what I'm saying right now. But let me just state it as a fact without spending too much time on this. So what we have seen is as follows. This G is the Grassmann graph, right? And we identified this set called S sub AW, right? And we observed that the expansion of this set is 1 minus 1 over 2 to the A plus B. Okay. And ideally, I would like to say that these are precisely the sets whose expansion is bounded away from 1. But that's not quite exactly true, but close enough. Okay. So it helps to point out the following fact, that if you take this set S sub AW, and inside that take a set S of constant density. Okay, so take a set S inside one of these S sub AWs, and just to emphasize, right, depending on, because A and W are just arbitrary pair of subspaces, so depending on what an A and W are, there are many different sets, right, of this kind, S sub AW. So pick any one of them, S sub AW, and then inside that take a set S of constant density, meaning its density is theta. Think of theta as say 0.1 relative to the size of the set S sub AW. Okay, then it's actually easy to show that even if you take a set of constant density inside of one of these special sets, the expansion still remains bounded away from 1. So you can show that the expansion of this set is at most 1 minus theta times 1 over 2 to the A plus B. Okay, this 1 over 2 to the A plus B comes from the set S sub AW itself, and then this theta comes from this density. Okay, but as long as theta is constant density, this whole thing still remains bounded away from 1. Okay, so yeah, so now if you account for this this minor additional detail, so now our list of sets whose expansion is bounded away from 1 right, we said, of course, these sets S sub AW, they qualify, but also those sets S which are constant density inside this S sub AW, these also qualify. Okay, and now more or less the theorem is that this is it. There is nothing more than this. Okay, these are precisely the sets of whose expansion is bounded away from 1 in the Grassmann graph. Okay, so now let me state the Grassmann expansion theorem. Okay, so here is the precise theorem. So this picture should be somewhat illustrative, somewhat useful. So this is the Grassmann graph G, the whole thing, and then there are these sets called S sub AW. Then there is S sub A prime W prime, S sub A double prime W prime, whole bunch of these, right, everywhere. And these are these special sets whose expansion is bounded away from 1. And the theorem is that if S is any set, S is this dotted set. If S is any set whose expansion is bounded away from 1, say at most 1 minus delta, then it must intersect one of these special sets in constant density. Okay, that's the statement. Okay, so so to be precise, for every delta there is a R and a theta, such that if you have a set of expansion 1 minus delta, then S intersects one of these sets S sub AW in density at least theta. So there is some set S sub AW for dimension of A little a, dimension of W k minus b, A plus b is at most R, such that the density of S inside the S sub AW is at least theta. Okay, so think of this as for every delta equals 1/10, right, there is some R, maybe R equals 5, and some theta, maybe theta equals 1/5, such that this holds. Okay, so this is the theorem. Now, I mean, if you're really picky, you know, you could complain that you still did not characterize what this set is. All you told me is that this set has constant density inside one of these special sets. Okay, but what about the whole remaining part of this set S? But turns out once you have this theorem, you can even obtain essentially full structure theorem. So what you can say is, okay, fine, you get this constant density piece inside one of these special sets, throw it out, and apply the same theorem again repeatedly to whatever is the remaining thing. So you just keep finding these constant density chunks inside the special sets, okay? And then once you cover constant fraction of the original set, then you stop, okay? And once you stop, it essentially explains why this set has expansion bounded away from 1. Okay, so you offer a near full explanation, and you get a full structure theorem. But that's a somewhat minor detail, so let me skip it and just think of this as the expansion theorem. Okay, so if anybody wants to just say that at least the statement of the theorem was clear.
Yes, clear to me.
Okay, very good. So yeah, now as the final like 15, maybe 20 minutes of the lecture, I will just try to give you this. It's very simple, but very nice, elegant proof that this expansion theorem implies the linearity testing theorem. Okay.
Subhash, just a question. When I was, I think, browsing through some of your papers, to me it seemed that that for the theorem, it would have been enough to characterize expansion below 7/8. Is it?
No.
Okay, then I'm okay. Thanks.
No. So maybe you looked at an intermediate paper where we characterized sets whose expansion was below 7/8. But that was our first paper. And then in the subsequent paper, we extended it to right, all sets of expansion slightly less than 1.
And the
so that turned out to be, yeah, it turned out to be much harder.
Okay, thanks.
Yeah, so what I hope to now show you is this quick proof that the expansion theorem implies the linearity testing theorem. Okay, And so just to quickly recall, this was the expansion theorem, right? That for any set whose expansion is at most 1 minus delta, it has a constant density theta inside some special set called S sub AW, right? And then the linearity test, maybe you forgot by now, so this definitely needs some reminding, right? That there was this test, right? That for spaces L, L prime, there was a table F, right? Assigning linear functions to L's and L primes. And the theorem was that if this table is consistent on delta fraction of the pairs LL prime, meaning on delta fraction of pairs LL prime, the linear function assigned to L and the linear function assigned to L prime was consistent on the intersection. If this happened, then it's possible to zoom in and out, right? Using a space capital A and space capital W, such that dimension of A plus codimension of W is at most R. So zoom in and out, meaning focus only on those spaces L which contain A and are contained in W. Once you do that, there does indeed a global linear function G, which is consistent with the given table at some constant fraction delta prime of the spaces L. Okay, so this was the linearity testing theorem. And now we will quickly prove that this implies this, right? The top implies the bottom. And of course, you would sort of go in the reverse, right? So you will say, okay, let's look at this table F. Okay, from this, you are going to sort of look at the Grassmann graph, and somehow in the Grassmann graph, find a set whose expansion is bounded away from 1. And this theorem will then allow you to zoom in or to figure out what this special set S sub AW is. And then that same AW you are going to use to zoom in and out, right? So that's the scheme. And as you will see, it's really simple proof. And I mean, I will give you like a quick, anecdote. So when we were working on this project with Dinur, Kindler, Minzer, and Safra, so I mean, we had everything in place except this one missing piece, right? Which was that this linearity, this expansion theorem implies linearity testing theorem. And when you are in the middle of this fairly serious chaos, right, you don't realize that what you were missing was actually quite simple. And yeah, so we were just too blind to notice this. And this particular proof that I'm going to show now, this is by Barak, Kothari, and Steurer. And then that was like the missing piece, right? So here is this nice proof. Right, so you have this table F, right, which has this delta consistency. And I'm trying to figure out how to use this zoom in and zoom out, A and W. Okay. Now, let G be a just random linear function on the global space. Okay, so let G be a random linear function. And let S sub G be the set of those spaces L for which G is consistent with the given table, right? So S sub G is all spaces L for which the answer which is given in this table, right? This table assigns some linear function to L. If that happens to be agree with G, right, then that L is in the set, otherwise it's out. So that's the definition of this set S sub G. Now, what's the expected size of this S sub G relative to the size of the whole graph, right? Now, this is clearly 2 to the minus L, because for any fixed L, the answer f of L, that's a fixed answer that's given there. And then what's the probability that it's consistent with G for a random function G, right? And on an L dimensional space, you are consistent with some fixed answer with probability 2 to the minus L, right? So expected size of this set S sub G is 2 to the minus L. Okay, so this is easy. Now we will also show that, I mean, relatively speaking, this set S sub G actually has lots of edges inside, okay? And the to be precise, expected fraction of the edges inside this set is 2 to the minus L times delta over 2, okay? Delta is the probability of acceptance of this linearity test, right? And here is the easy proof. So let's focus only on those pairs L, L prime, for which the answers f of L and f of L prime are consistent. And we are told already that this consistency happens on delta fraction of these pairs. Okay, and we will basically show that on these pairs, if L is inside S sub G, it's very likely that L prime is also inside S sub G. Okay, and this is for the following reason. Let L, L prime be any such edge on which the two answers f of L prime are consistent. Fraction of such edges is at least delta, as I said. Now consider the probability that L, L prime both are in S sub G over random choice of G. Now, what's the probability that L is in S sub G? So that we already said, right? That the probability that the given answer f of L is consistent with G is 2 to the minus L. This we already said. But then turns out, conditional on L already being in S sub G, then L prime happens to be in S sub G with very large probability, with probability half. Okay, and this is because on that pair L, L prime, the answers f of L prime and f of L, they are given to be consistent, right? So these are linear functions f of L and f of L prime, which are consistent on L intersect L prime. And now, if G was consistent with L, okay, then G was also consistent with L prime already on the intersection, right? So for G to be fully consistent with L prime, it would need to be consistent on L prime only on this one extra degree of freedom, right? Which would happen with probability 1/2 because G is a random function. Okay, and this is really the key point, that once L is in the set S sub G, it's very likely that L prime will also be in the set. Okay, so what's the expected fraction of the edges inside this set? With probability 2 to the minus little l, the left vertex L is in the set, and once the left vertex is in, the right vertex is in with probability 1/2. Okay, and then you have to account for this delta, because only on delta fraction of the pairs we can carry out this argument, right? Because we need the answers FL and FL prime to be consistent with each other, and that is happening only on delta fraction of the pairs. Yeah, so the fraction of edges inside this set is 2 to the minus L times delta over 2 in expected sense. And also, as we already said, the in expected sense, the size of this set is 2 to the minus L, right? So yeah, and basically you can pretty much ignore this expectation. You can do more careful argument if you want, but you can effectively just ignore this expectation. So this is a set S sub G whose size is 2 to the minus L, and the fraction of edges inside is 2 to the minus L times delta over 2. Okay, and this means that its expansion is at most 1 minus delta over 2. Okay, right, because it has lots of edges inside, therefore its expansion is bounded away from 1 minus delta over 2. And this happened in expected sense, but I can certainly say that there is some choice of G, call it G star, such that expansion of the set S sub G star is bounded away from 1. Okay, yeah, so I hope this was clear. It's really simple. Okay, and now once I have a set S sub G star whose expansion is bounded away from 1, I can just use my expansion theorem, right? Which states now that whatever this set is, it must have constant density inside one of these specialized sets called S sub AW. Okay, so using the expansion theorem, there is some A and W's whose dimension plus codimension is at most R, such that the set S sub G star has constant density inside this specialized set S sub AW, the density being at least theta. Okay. And then that's it. We are basically done, right? What we are really looking for is just, right, it's just writing in different notation. So yeah, so you are measuring density only inside this set, right? So you only want to take the probability over choice of a space L, which is in this set, right? S sub AW, and then it should be in S sub G star, right? That L should be in S sub G star, but which is same as saying that the G star is consistent with the table F on the space L, right? So this is exactly the statement that once you zoom into only those spaces L which contain A and are contained in W, then there is a global linear function G star which has consistency with the given table up to some constant theta. Okay, and that was the proof of the. This is the conclusion that we needed for the for this Grassmann linearity test. Okay, so as I said, I mean, this is a very nice, quick and nice proof. And I will effectively end here. So in the lecture notes, there are, roughly speaking, 2 more modules, which you can look them up if this interests you. And everything also appears in this survey article that I wrote. And these 2 modules are, firstly, so in this Grassmann expansion theorem, to prove the full theorem, it characterizes sets whose expansion is bounded at even slightly less than 1. Okay, but if you take a very, very special case and consider sets whose expansion is about 1/2, okay, then the proof is not that difficult, and it's actually quite illustrative in terms of how to use eigenvalues and right, and how to also use the eigenvalues of the Grassmann graph and what the corresponding eigenspace is, and the Fourier analysis on the Grassmann graph. Yeah, so that even the simplest case of sets of expansion close to half, that's already quite illustrative, and that proof does appear in these notes as well as in this written survey article. So that's one module, and then the second module is how to use these Grassmann linearity test actually to prove the correctness of the reduction from 3-lin to the 2-to-2 games. Right, and that at least, I mean, that's the details there are actually not completely straightforward, and we actually had to do several things there which were quite new, and they were never done before in the PCP hardness world. But at least in these lecture notes and this written article, you should be able to at least get an overall sense of what the reduction looks like. Yeah, so you can look these things up if this interests you. And yeah, and I hope overall, I mean, this set of 5 lectures did give you good idea of what this topic is about. And even though I mean, it's perfectly reasonable and fair that right, I might have lost some of you at least for some period during the 5 lectures. That's perfectly okay. But I hope this was beneficial and it gave you some good sense of what everything is about. Right. Yes, I will stop here.
Thank you, Subhash, for this lecture. It was a wonderful finale. Are there any questions? So, if not, then since this was the last lecture of this lecture course, let me make some final remarks. Firstly, I would like to thank our scientific board for the suggestion to invite Subhash. I think that was a very fortunate suggestion. I would also like to thank all of you guys. I think that the course required quite a lot of study for many of you, and I hope that it will help you either in your own research or just in understanding what your colleagues are doing, which is often equally important. And last, but most importantly, let me thank Subhash for delivering this course. It was a privilege for us as organizers to host such a course, and we really appreciate your time, Subhash, and the energy you put into preparing all this material. So
yeah, my pleasure, and thanks for inviting. Actually, nothing makes researcher happy than some bunch of people who are willing to listen. So
okay, yes, as I said, the pleasure was on our side. So I invite everybody to unmute themselves and thank Subhash for with applause for this wonderful lecture course.
lot. Bye then.
Thank you.
And good luck to everybody in your academic and research careers. Bye.
Thanks. Bye. And let's meet again in half an hour for science course, and I will also see some of you for the last exercise session either tonight or tomorrow. Okay, so see you.